mathematical understanding of what it means for a graph to have a horizontal asymptote. In terms of applications, it's often thought of as what happens to something in the long term or in the long run, like populations stabilize, economies maybe stabilize, maybe populations go extinct. So it's a very useful idea of limit. It's also a tough one. Up to where we've gotten so far, it's probably the hardest of the limit ideas that we're going to look at. So we might get started on it today, depending on if we can finish up working with continuity. So, what's this? So yesterday we basically talked about what it meant for a function to be continuous at a point, what it meant for it to be continuous on an open interval and a closed interval. Remember, continuity on a closed interval. On the left-hand endpoint, it's right-hand continuity. You got to come from the right. The right-hand endpoint, it's left-hand continuity. You have to come from the left. And we talked about, without proving it, virtually all of the functions you're familiar with, all of the simple functions, are continuous on their domains. And the root functions and the inverse, some of the inverse trig functions have domains which have endpoints. So we're looking at the one-sided continuity for those functions. And then if you take functions and you combine them in the natural ways of adding, subtracting, multiplying, and dividing, those functions will be continuous on their new domains. Now their new domains, like the one problem we did, could be a very small interval, or they could still be all real numbers. The one thing that we haven't talked about in terms of how we produce continuous functions from other functions is composition. Now there's a preliminary result, again something that we do not prove, which will turn out to be a very useful idea. It will occur not only in this course, but also in Math 1B. And that's the idea of taking a continuous function of another function. That second function may not be continuous, but it may still have a limit as x goes to some number. So this is kind of a standalone theorem, and it has a surprising number of useful applications. We'll see a couple of those in just a minute. So we're still doing continuity. Is it true that compositions of continuous functions are continuous? So we're going to answer that by first of all looking at a more general situation and showing how nice it is to have that general situation, and then we'll be able to take care of the fact that yes, compositions of continuous functions are continuous. So, theorem. So suppose f is continuous at b, and the limit as x goes to a of g of x is b. Now we're not saying that b is equal to g of a. We're not saying that g is a continuous function, but we are saying that it does have a limit as x goes to a from both sides. So f is continuous at b, limit as x goes to a of g of x is equal to b, then the limit as x goes to a of f of g of x is equal to f of b. More importantly, it's equal to f of the limit as x goes to a of g of x. Now this seemingly last statement here, seemingly innocent last statement, is extraordinarily useful. Conclusion. You may pass the limit symbol through a continuous function. So that's what this really says. So you got a function in here, it's composition, f of g of x is composition, and the outside function is continuous at the limit of the inside function, so you can move the limit symbol through the continuous function, go ahead and find this limit, and then evaluate f at that limit. So a couple of examples just of that. And you'll see more of them, especially when we get into chapter 4, and we're doing L'Hopital's rule. You'll see a lot of this. Now x plus 1 over x squared minus 1 is not a continuous function. It's undefined at 1. But e to the x is a continuous function, so we can move the limit symbol up above and that's actually that limit we looked at from the very first day. We now know we can find it by factoring and reducing. Oops. And then minus 1, sorry. So we're looking at e to the limit as x goes to minus 1 of 1 over x minus 1, and now that can be done by direct substitution. We get e to the minus 1/2, or 1 over the square root of e. So it's very useful to pass limit symbols through continuous functions and attach them to the place where you're going to have all the action. And after all that's done, then the continuous function just evaluates itself at that particular value. Here's another one. So the limit as x goes to 1 of the arctangent of x minus 1 over x squared minus x. Now arctangent, that's the same as the inverse tangent, just another name for it. It's an inverse trig function, it's continuous on its domain. As long as this limit is in the domain, that's going to be fine. Can anybody tell me what the domain of the arctangent is? Or inverse tangent, what's the domain? Domain of inverse tangent. All real numbers. It's the one that's really important because its domain is all real numbers. So as long as that thing inside has a limit, we'll be in good shape. So it's a continuous function. We pass the limit symbol through. Limit, x goes to 1, x minus 1 over x times x minus 1. X's cancel. So arc tan of limit as x goes to 1 of 1 over x. That's the arc tangent of 1. You can tell me what the arc tangent of 1 is.
Pi over 4.
Pi over 4. So just a couple of examples to illustrate how this theorem can be used to find limits. Again, the outer function has to be continuous at the limit of the inner function. The inner function does not have to be continuous. In fact, this theorem also works for one-sided limits. If x is going to a from below, and g of x has a limit as x goes to a from below, then you can use this theorem as well. So it's a very useful theorem. It's actually much more useful than the main idea that we wanted out of this, which is, can we show that a composition of continuous functions is continuous? And we can. So let's do that. So I'm using our well agreed upon symbolic expression for composition. Here's what we need to prove. This is a very easy thing to prove now.
Sorry, what does that mean?
I'm sorry.
Right there, the
F fog.
yeah.
F of G.
F of G. Okay.
That's your old composition, symbolic composition from Math 27, college algebra. So that's just f of g of x. But since that is used in your text and other texts, I'm deliberately confusing the issue by using it. Because you're going to see it, so you better know what it means. So here's what we need to show. We need to show that the limit as x goes to a of f composed with g of x is equal to f composed with g of a. So that's what we're supposed to show. So we'll start over here on the left. So this is equal to the limit as x goes to a of f of g of x. Now, since g is continuous at a, the limit as x goes to a of g of x exists, so we can move the limit symbol inside using our theorem. And again, g is continuous at a, so that is f of g of a, and we put that back into the confusing symbolism, and that's what we needed to show. So the key step was that theorem. So now when we add in, taking a collection of continuous functions, adding them, subtracting them, multiplying them, dividing them, composing them with other continuous functions, we have a monumental bag of functions, all of which are continuous on their domains. So you might say there's nothing left to do then. There's nothing left to think about. We're done. The subject continuity is completely done. Not true. Because we know what happens with the basic functions, the root functions, inverse trig functions, and so on. We know what happens with them. We now know what happens when we abstract, multiply, divide, compose, do algebra things to them. But what we don't know yet is what happens when we take them apart into pieces and stitch them back together in piecewise defined fashion. And surprisingly enough, the piecewise defined functions in the real world are among the most useful and most frequently occurring. Just think of parking rate structures, think of tax tables and so on. Those are all piecewise defined functions. So if I take some of these functions that have nice continuity properties, and I put them together, and I make piecewise defined functions, are those functions still continuous? And some of them will be, and some of them won't be, but now we have to prove that they are, or show that they aren't. So there's our next step. So let's work with that a little bit. So who thinks they know how we would proceed? So we have a reciprocal function, a constant function, and a linear function. We know that the constant and linear functions are continuous on their entire domains, which are all real numbers. We know that 1 over x is continuous on its domain, and that's all values of x except 0. So, how about all the numbers that are not -1? Can we state with no work that if x is not minus 1, this function is continuous?
Yeah.
We sure can. Because this function has two-sided continuity for all values of x less than 0. We're only using it for x less than minus 1. So when x is less than minus 1, that is absolutely continuous. When x is greater than minus 1, here's another function. It's a polynomial function. It has two-sided continuity for all real numbers. So x less than minus 1, continuous. X greater than minus 1, continuous. So the only place where we have to worry is minus 1. So f is continuous for all x not equal to minus 1. What about minus 1 itself? So there's our problem number. So is it continuous at minus 1 or not? How do we find out? What do we do? Yep.
Take left and right-handed limits.
Right, we've got to do left and right hand limits. Got to do it. So, the limit as x goes to minus 1 from below of f of x is the limit as x goes to minus 1 from below of 1 over x. Now this function is continuous at minus 1. So if the two-sided limit exists, the one-sided limit exists, and you can obtain it by direct substitution. So that's minus 1. So the left-hand limit is minus 1. Now from the other side, that's 2 plus 3x. Well, once again, this function is continuous for all real numbers. Its two-sided limit can be found, and therefore any one-sided limits can be found by direct substitution. So this is 2 plus 3 times minus 1, which is minus 1. So we have, the limit as x goes to minus 1 of f of x is minus 1. Have we shown that it's continuous? What's the one thing that's missing? It's got the two-sided limit, got to have that. But what has to happen for it to be continuous? It has to be equal to f of minus 1. But f of minus 1 is equal to 2, which is not equal to the two-sided limit. So it is not continuous at -1. It's continuous, not constant. Okay, so it has one point of discontinuity. Now the question is, can it be removed? Usually you want to know if it can be removed, but you don't necessarily remove it. You just want to say, is it removable or not? Normally you would want a reason to remove it, and if you didn't have a reason, you'd probably just say, leave it alone, but it is removable if I need to do it at some other time. So removable discontinuities. There's only one situation in which a discontinuity can be, quote, removed, unquote. What about this situation? Is this a removable discontinuity situation? We talked briefly about that the other day. Remember problem 53 of yesterday where we had the greatest integer in x plus the greatest integer in minus x, And we showed that the two-sided limit existed as x went to 2, and it could have been other numbers, but it wasn't equal to the value there. That was an example of a removable discontinuity. We didn't remove it, but we could have. In a way, when you think about removable discontinuities, you're thinking about a function which is sort of accidentally not continuous. Everything is fine, but at the place where it should be continuous, either somebody deliberately, which is what I did here, redefine it so it's not continuous, or maybe it's a place that's not in the domain of the function. Basically, the only time you can remove a discontinuity is when it comes from a hole in the graph, two-sided hole. So everything is fine, the one-sided limits both exist, are equal to the same thing. We have a nice two-sided limit, but at that spot, either the function is somewhere that it shouldn't be, or we don't have anything there. So removable discontinuities occur when the two-sided limit exists, but it's not equal to the function value itself. So this is removable. And if somebody said, okay, show me how to remove it, here's what I would do. I would keep this function exactly the same for all values of x not equal to -1. Remove it by leaving f of x alone, x not equal to -1, and we set f of -1 equal to the common limit. So instead of letting it be 2, which was sort of a deliberate on my part to make it removable, instead of letting it be equal to 2, we let it be equal to the common, the value of the two-sided limit. Then, at this place here, now that we've redefined it, this is now equal to the two-sided limit. What we did basically is we filled in the hole and got rid of the dot at 2. So the main thing I want you to be able to do is when you look at a function that's not continuous, to be able to decide whether or not it's a discontinuity that's kind of accidental. It could be removed, or it's fundamental. So all the other discontinuities are fundamental. Two different one-sided limits, you can't do anything to the function value there to make them come together. They are fundamentally ripped apart. Vertical asymptotes, infinite oscillation. You cannot remove those discontinuities. So only when the two-sided limit exists is it possible to do that.
So if it's two-sided, you didn't know automatically that's removable.
If the two-sided limit exists, that discontinuity is removable. Correct. Again, whether or not you remove it is not the point. It's possible to do so. All you do is redefine the function to be equal to the two-sided limit. So it's simple to do, and now all of a sudden it's continuous. you're gonna see a couple homework problems like this. Where C is what we call a parameter. It's a fixed number, but it can be any real number at all. And so it's used in both of these functions. The first one is a nice simple linear function. The second one is a quadratic function. For most values of C, the two graphs would not meet. They would have a fundamental finite break discontinuity. But possibly for one or maybe more values of C, those graphs could be connected. Now this is a problem where it's very easy to get the right answer and get a 0 on an exam or a homework problem. Because if we want to make it continuous, we have to satisfy the conditions of continuity. First, the two-sided limit has to exist. Since we have two different functions, we have to do two one-sided limits. Secondly, after we've done that, then we have to make sure that whatever value of C we select to make the two-sided limits equal is actually the value of the function at the number 1. And 1 is the problem number again. This is continuous for all numbers less than 1 because it's actually continuous for all real numbers. Another polynomial, continuous for all numbers greater than or equal to 1 because it's certainly continuous for all real numbers. But the question is, the changeover point at 1 is the problem. Is this function continuous at 1? That's the only place where there's an issue. And again, because there's two different functions, we're going to have to look at two different one-sided limits. Limit as x goes to 1 from below. Cx minus 1, again, this is a polynomial function. C is a fixed number. It's continuous everywhere. We can evaluate both two and one-sided limits by plugging in the number 1. So there's the left-hand limit. Again, another function which is continuous for all real numbers, so either two or one-sided limits can be figured out by plugging it in directly. We plug in 1 directly, we get minus 2 plus c squared. Now we need to find a value of c, or maybe a couple of values of c, that make those two one-sided limits equal. So we have a quadratic equation to solve. The c's cancel out. Add 1 to both sides. And so it looks like there are two values of c, each one of which would make the function continuous. So let's suppose what you did on your first exam. Suppose I put this problem on your first exam, and you did exactly what I saw right there. Would you get full credit?
No,
Why not? What didn't you do?
you didn't remove it. You didn't prove that it's.
Well, but let me put it this way. Well, okay. You are correct. I didn't prove that it's no longer removable. I need to show that those two values of c produce something that's a solidly continuous, not something that I then have to remove. So what have I not done that I have to do?
Plug it back in the original function and see if they work.
I have to go ahead
Yeah.
and find out if that two-sided limit is equal to the value of the function. So, where do we get the value of the function at 1? We get it here. So this is the value of the function at 1. So notice, because that's where the equals 1 is. So note, f of 1 is minus 2 plus c squared. Now our equation says that f of minus 1, the limit, it's a two-sided limit now, is going to make this equal to, this quantity is going to produce the two numbers that make the limit equal. So that means that when c is 1 or c is minus 1, the limit, of course the one-sided limit is going to be equal to f of 1 because that's on this side, but it's equal to the other one-sided limit. So the limit as x goes to 1 of f of x will be equal to f of 1. You always have to make sure, because I could have got rid of the equals here, and I could have put something here at 1. And then after you've gone through all this work and made the two one-sided limits equal, you might say, yeah, okay, fine, but for those values of c, do I get that number right there? But fortunately in this problem, I included the 1 on one of the two functions. So all I have to do is make sure that when I plug 1 into this function, it's going to be equal to the two one-sided limit. Well, here are the two one-sided limits, and that's one of them. So that's guaranteed. But if you don't do that, then I would say you didn't take that final step. You didn't show that the two-sided limit is actually equal to the value of the function there. And that's a pretty common mistake. People just kind of blow that off. So both values of c, i.e. 1 or minus 1, produce full continuity. So again, this always make certain two-sided limit is equal to the function value. So again, you might say, well, that was built in, that's going to happen because I put the little equals there, but you got to show me that you understand that. Now, if you put these on a graphing calculator and graph them for like 100 values of c, you would find out that they almost always have a gap, except when c is 1, the gap is closed, and when c is minus 1, the gap is also closed. It's closed at a different place, a different value of f of x, but still it's closed for those two numbers and not for any other two. Before I leave this problem, let me stress, again, I'm thinking about common mistakes that have occurred on my first exam in Math 1A. When I do a problem like this, and I almost always do one, common mistakes that occur. People just look at this, they plug 1 in there, they plug 1 in there, so they go straight to here, and then they're done. Well, you haven't shown a thing. Because you can't show continuity if you don't do limits. So if there's no limits on your paper, that would be a 0. If you get the right answer, you get no credit at all. So for piecewise defined functions, continuity at a place where the functions change can only be done by 2 one-sided limits and making sure they're equal to each other and the value of the function. So it's a little complicated. It's real easy to get the right answer and get no credit. So be very careful about that.
So you keep in mind that first you prove it, or first you solve it and then prove it.
Well,
It's like check.
well, actually, you do them simultaneously. You calculate the 2 one-sided limits. If it's going to be continuous, they have to be equal. That gives you the value of C. Then once you've got those values of C, you make sure that if you use those values of C, that would be the value of the function at 1. So you go through that full process. Even if you can get the answer in your head. So I'm going to draw a graph. And we're going to focus only on those values of x where the function is not continuous. We don't really need any y scales because we're only interested in the x values. That's -1, -2, -3, -4. 0, 1, 2, 3, 4, 5, 6, 7, 8. So there's our function. What is this supposed to represent? It's hard for me to draw it by hand.
Oscillation?
That's an infinite oscillation. Okay. So Notice that this is the end of the domain. So the domain of this function is bracket 4, -2 parentheses, -2, 0 parentheses, 0 parentheses to 2 parentheses, 2 parentheses to 5 parentheses, and then 5 to infinity. So in terms of domain continuity, would we consider our function to be continuous here?
Yeah.
Yeah, it's got right-hand continuity, and so we would consider that to be continuous. Now, if I put a hole there and a dot up there, then it wouldn't be. So the first place where we have a problem is right here. We have a vertical asymptote. From the left, it blasts off to -infinity. From the right, it does go to a nice, it does go to a value at -2, but is the function, this is inside the domain, is the function continuous? And I say it's in the domain because it's just defined there. So since it's in the domain and there's values of x on both sides, it's got to be two-sided continuity. What do you think? No. So x equals -2. Where's another discontinuity?
X equals 0.
0.
X equals 2.
X equals 2. And
I'll see you pulling.
x equals 5. What about this thing here? Is that okay?
No.
Continuity, is that okay? Fine, continuity. Later when we talk about differentiability, it won't be fine. Continuity is fine. I can put my pencil here and go all the way down here and keep going. I never have to lift it off paper. Okay, are any of those removable?
2.
0. Now, 0 for sure, because the only problem is two-sided limit is fine, but the function wants to go there and somebody put it down there, so that one's removable. So x equals 0 is a removable discontinuity. Now at 2, there's a break. So no matter where you put that dot, you can move it from here to here, you can put it anywhere, you can put it up there, you can put it down there. You'll never make those two one-sided limits come together. So that is not removable. And neither is that, and of course, neither is that. So again, they're only removable when there is a isolated hole in the graph, in the two-sided limit, and the only problem is the function didn't fill in the hole. Okay, so any questions? Anybody?
How would that look on interval notation? Do we have to, there aren't any unions before that between them?
Well, if I were to ask you, what are the intervals over which it's continuous? If I were to ask, that's a different question. Then this would be bracket -4, comma, -2 parentheses. And then you do have right-hand continuity here, so it'd be bracket -2 up to 0 parentheses. Parentheses 0 up to 2 bracket, because you got right-hand continuity there and so on. But this is a simpler question. You know, just tell me where it's discontinuous. I'll be asking you that type of question on the exam. Now, many of the most important facts in Math 1A are facts about continuous functions. we have three what are called value theorems. We have an intermediate value theorem, we have an extreme value theorem, we have a mean value theorem, and in every single case, it begins with a function f is continuous on a closed interval, bracket a, comma, b bracket. They all begin with that. And then they throw in additional things. So, only the mean value theorem, which we won't look at until we get to chapter 4, after you've already had 2 exams and lots of homework quizzes and things like that. When we get to one of these that we can actually prove. And the mean value theorem is the most complicated sounding of the theorems. For our purposes, it may very well be the most useful one, but it's the only one that has an easy proof. The other two, the proofs require a bunch of stuff that you would not normally get in a regular calculus sequence. So here's the first one. Now, for example, if, let's say we came up upon a quiz that included the assignment where you were supposed to read about this, the assignment on continuity. And I have said that I could possibly ask a question from the reading at some point. So a typical question would be, state the intermediate value theorem. Just tell me what it says. I wouldn't say something like on page 12, paragraph 3, what's the first word? I'm not going to do anything like that, right? But I'm not going to ask for, tell me what the author says about whatever. But theorems, especially really important theorems, those would be fair game. So the intermediate value theorem has a fairly simple beginning. Suppose that f is continuous on closed interval a, b, and n is any number strictly between f of a and f of b. Now, strictly between means it's not equal to f of a and it's not equal to f of b. It's between them. So if f of a was 2 and f of b was 5, it would be some number bigger than 2, less than 5. Now, this is the number that gives the theorem the name, intermediate value. We think of n as an intermediate value between f of a and f of b. So here's the conclusion. Then f of c equals n for some c in the open interval a to b. So in other words, continuous functions acquire all of their intermediate values at least once.
It could be anything or would...
Anything in between. Now it tells you that it happens, it doesn't tell you how to figure out where it happens. So your ability to actually find out the C that works could be algebraically impossible. So if you want to find out where a 5th degree polynomial function crosses the x-axis, in other words where it's equal to 0, that's been shown to be impossible by use of any formula that you would recognize as a formula. So algebraically, you can't do it. Now, you can use computer programs to approximate it to 1,000 decimal places if you want. And as far as doing something with it other than theoretical, that would be as good as you'd ever want it to be. But to actually find it and say, here it is, it's cube root of 7 minus 5th root of e plus pi factorial or something like that, you're not going to be able to do that. So if this was a 5th degree polynomial function, and this was 0, it says this happens, but it doesn't tell you how to find it. You might think, well, if it doesn't tell me how to find it, then how could it ever be of any use at all? Using the intermediate, using any of these theorems, even the mean value theorem, which will be the most useful one, is kind of challenging. So here's what I would call a picture explanation. It most certainly is not a proof. So picture explanation. There's my f of a, and let's say here's f of b. So f of b is up there, f of a is down there. Now pick any number between those two, any one at all. Close your eyes and point. Let's suppose you ended up pointing here. So drawing this line here, y equals n. Now remember, it's a continuous function, so we're going to start here with our pencil. We're going to trace the graph all the way through until we get to there. Is there any way we're going to be able to not cross that line? You might say, well, I just won't cross it until but you know, I got to go from there to there. I don't care how, don't forget it's a function. I can't do it on a vertical line. So, darn it, I'm going to have to cross it. And there would be the C that we're talking about. So you can't possibly graph from f of a to f of b without crossing every horizontal line in between at least once. And that's what it says. And for most people, that's all they need. They're convinced. They don't have to see the actual proof. Now the question is, what are we going to do with it? How is it going to help us do anything at all? Well, believe it or not, it's going to help us prove the fundamental theorem of calculus, which we will prove, since it's the most important theorem in all of calculus. And we will use the intermediate value theorem to help make that work. For right now, the examples of the intermediate value theorem are fairly theoretical. Some books make a very big deal out of it. Your book doesn't make a big deal out of it. There's a few questions, and most of the time what these questions do is they have you show that an equation has a solution. Not that you could find it, but you show that it exists. So, what can the IBT do for us? Well, here's something that might make you a little interested in it. Does anybody know for sure that there really is a number that's the square root of 2? It's an irrational number. You cannot write it as a decimal. You can't produce it except to write it as a symbol. Maybe it's not really there. You think? Maybe it's actually not really there. Now there's some nice geometrical ways to show that it's there, but then we could move on to, you know, the 17th root of pi plus e. Does that really exist? And you wouldn't be able to show that with any kind of geometry. So let me do one of these problems. Prove that x squared equals 2 has a solution. Now we know that there's two solutions. One we call the positive square root of 2, the other one we call the negative square root of 2. So I'm going to show you using the intermediate value theorem that there is a number that makes that equation true. So here's what we do. We put 0 on one side, so we rewrite as x squared minus 2 equals 0. Then this becomes our function. Let f of x equal x squared minus 2. And our job now is to find an interval where one end of the interval, that function is negative, and the other end, it's positive. If we can succeed in doing that, then 0 is an intermediate value. And the intermediate value theorem says there's a value for x that makes that function equal to 0. So this is a certain amount of trial and error, but not too much. So f of 1 is equal to minus 1, that's less than 0. And f of 2 is equal to 2, which is greater than 0. So on the interval 1 to 2, IVT says there is a C such that f of C is 0. So 0 is between those two numbers. So 0 is an n for the intermediate value theorem. 0 is often the number that's used, though not always. But generally, if you're trying to show that an equation has a solution, then you want to rewrite it so you have 0 on one side. Again, because f of 1 is less than 0, which is less than f of 2. So 0 is an intermediate value. So it's guaranteed that there's a solution. Of course, which one is it? What's the solution in this interval to that equation? Is it the positive square root of 2 or the negative square root of 2?
Maybe negative.
So it's an interval of positive numbers, so it would have to be the positive one. Had I selected different numbers, I would have got the negative one. And f of c is c squared minus 2. Intermediate value theorem says that's equal to 0. And that says that c squared is equal to 2 for some number in 1 to 2. Then you can go ahead and call it the square root of 2 if you want. So if you believe in the intermediate value theorem, if you believe that it's true without having seen its proof, but I do think that the picture explanation makes it pretty easy to swallow, then there has to be a number whose square is 2. Whether we can find it or not or understand it, it has to be there. Now you can use this to show that certain equations whose solutions you wouldn't even have names for have to exist. Like, when is the tangent of x equal to x, for example? There's an infinite number of solutions. There's only one that you know, which is 0. So you can show that that equation, tangent x equals x, has solutions in many different intervals by using this idea right here. So one thing that the IVT does is it shows that equations that you could not solve, and nobody will ever be able to solve them algebraically, that they do have solutions. If you know they have solutions, you might try to figure out ways to approximate them. But it's not the only thing it's good for. It's good for other things. It's also good for showing things that are very hard to believe. Like, for example, here's something that the intermediate value theorem could show you. At any moment, any time of the day, there are 2 points on the equator that are exactly opposite each other that have identical temperatures. Identical. Not about the same, identical. That doesn't sound possible, right? How could you ever imagine that there's some point on the equator, and if you go all the way across the center of the Earth to the other point, that point over there has exactly the same temperature as the one you're at? Now, that might only happen at one point, it won't happen at more than one, and it might only be for one instant, but it always has to happen. And that's a consequence of the intermediate value theorem, believe it or not. There's a whole bunch of really cute, clever things that you find very hard to believe that are true because of the intermediate value theorem. Anyhow, those things make people a little more interested in it. So for us, it's there. You got a couple homework problems showing that certain equations have solutions, but other than that, we won't find ourselves needing it for a while. Sure.
You know where that point is?
Well, it changes with every instant. And don't forget, proving that there is a point doesn't mean you can find it. Right? But you can show it has to exist. Okay, we've got 5 minutes, so let me just touch on the idea of limits at infinity. So everybody is familiar with horizontal asymptotes. Exponential functions have graphs with horizontal asymptotes. Many rational functions have graphs with horizontal asymptotes. And the idea of a graph of a function having a horizontal asymptote is essentially the idea of a function having a limit as x goes to infinity or minus infinity. So these are called limits at infinity. So this is just the beginning of 2.6. I'll just throw in a couple of pictures and then we'll be done. So we say that the limit as x goes to infinity of f of x is equal to L. The further out we get, the closer the graph gets to L. It may or may not cross it many times, but it just gets closer and closer and closer. If you go far enough out, even though it isn't actually on the line, it looks like the line is so close. So that's a limit for positive infinity. And here's a limit for negative infinity. In this case, we say that limit as x goes to negative infinity of f of x is equal to L. And again, all it means is the more negative x gets, the closer f of x gets to L. Now, most of your limit laws work for limits at plus or minus infinity. There are a few that don't, but most of them work. Think of these as one-sided limits. That's going to positive infinity, that one's going to negative infinity. So that one's going to the right, this one's going to the right, that one's going to the left. So we'll explore finding limits at infinity tomorrow. So if you haven't already done so, be sure you read chapter 2, section 6, so you come to class ready to go.